Welcome back to our course on Principle and Applications of Fluorescent Spectroscopy. This lecture is going to be a follow-up on the previous lecture where we described all the different probes and how they're affected by solvent. Today we're going to consider the time-dependent spectra that might result from this. I put this as a separate lecture because I thought it would have been too much to include just with the lecture on fluorescent probes. Let's start by looking back at the Lippert scheme that we discussed in part 6, and that is where the fluor starts in the ground state with the ground state solvent orientation of all of the solvent molecules, goes to an excited state, but that's instantaneous, so we keep the ground state solvent configuration. Then there's a relaxation rate, which we assumed to be very fast in the previous lecture, where the solvent molecules reorient around the new dipole moment, and then emission to the ground state, also instantaneous, same distribution of solvent, and then to the equilibrium state. We made a large assumption while we were talking at all the probes, and that is that we assumed that the solvent relaxation rate was faster than the emission lifetime. So we assumed that this process was complete and we're only observing emission from this state. But what happens if the relaxation rate is comparable to the lifetime? That puts us under a very different set of conditions. And first we'll consider another slide from the previous lecture, which was the emission spectra of protan in phospholipid vesicles below and above the phase transition. These are peak normalized, and was a very large shift in the emission spectra. So what's happening to the spectra during this time? Are these spectra from a completely relaxed state or from some relaxation process that was in progress as we were recording the spectra? To explain this, let's start with a simplified diagram for spectral relaxation, where we just have the molecule going to the excited state. It can emit or it can relax. If this solvent relaxation rate is very quick, all we observe is the completely relaxed rate of the fluorophore. We don't see emission from the initially excited state, which would have been here at shorter wavelengths. So let's compare the effects of fast and slow relaxation. Fast relaxation we just described. Slow relaxation, we have this solvent relaxation rate comparable to the lifetime, and so the fluorophore can be emitting at the same time as going to the relaxed state. So now we observe some different emission spectrum, which is intermediate between the F and the R states, and this is because of the mixture of the processes of relaxation and emission. There are really two possible models for this. The first is the continuous model, which is the one we sort of just discussed, where the relaxation is continual while the molecule is in the static state. It's going to be easier to explain this process by starting with this two-state relaxation process, where the molecule goes to relaxed state, which has a longer emission spectrum than the F state. So during the lifetime of the excited state, the F state is decreasing in intensity and the R state is increasing in intensity. What do we expect for the time-resolved emission spectra? I thought it might be useful to make a prediction ahead of time of what we might expect. So if it's a continuous relaxation, and we could collect the emission spectra at 1, 2, and 3 nanoseconds, which we're not able to do. We have to reconstruct these, as you'll see later. We expect to see the same emission spectra, just shifting along the wavelength axis. If it's a two-state process, we expect we might see separate emission in the time-resolved emission spectra. At the first shortest lifetime, only see the F state, then see a mixture of the two states in the intermediate time, and only the relaxed state at longer time. We'll show you some of these time-resolved emission spectra as we go along. This is purely for the physical chemists who might be watching this and are thinking, what's this guy talking about? So I just thought I'd show off a little bit and say that we have a reaction coordinate for the continuous state where the molecule can be emitting during the process of relaxation, or in the two-state process that we have two different minima in the excited state, and the F state is going to the R state. But we wrote it as K1 here. We really mean the rate of relaxation. So let's start with a very simple case, which is 2-naphthol, which provides a great example of a two-state reaction, and I think that's easier to understand. So naphthol has a pKa at a pretty high pH value, but when it's in the excited state, the pKa drops sharply down from 9 to 2. So in neutral solution, this is all we have, but when we go to the excited state, the naphthol will immediately start to lose protons. And so we expect this two-state model. So just to get you oriented, what do the spectra look like? And we're really interested in the unionized and ionized states of naphthol. So this is naphthol and naphthalate. And I specified two wavelengths at the bottom. Well, we expect this to be this state to be shifting to this state with time. And I indicated these two wavelengths because we're going to present intensity decays at a couple of different wavelengths, but I'll mention those two. So in order to get the time-resolved emission spectra, what we have to do is to collect the time-resolved decays across the emission spectrum, and we notice something immediately. When we look at the naphthol emission only, which is at 335, we see a more rapid decay than we see at 485, which is the relaxed state. The reason for this is at the shorter wavelength, the naphthol is decaying not only by its normal excited state reaction, but by the loss of a proton. So that's depopulating the first excited state more rapidly. At longer wavelengths, first thing we notice is that we see a rise in the intensity before decay, and that's because at time equals 0, there's no naphthalate. It's all in the protonated state. But then as it relaxes to the naphthalate, or the ionized state, we have a slower decay because we're looking at this state, which has to be derived from the initial naphthol. A rising intensity is a proof of an excited state process. So if you're looking at any set of data and you notice a rise with from the beginning, that would be stated in the decay law as a negative pre-exponential factor. That's an absolute proof of an excited state process. But the converse is not true. It doesn't always show up, and it's not always observed, but it's nice that when you can observe it. And here are the reconstructed emission spectra for naphthol. So we took the time-resolved emission decay, and by using a set of equations which are too complex to present in this type of lecture, we see that the naphthol intensity decreases rapidly with time. The naphthalate emission increases as time. It doesn't increase as much because the naphthalate quantum yield is smaller than the naphthol quantum yield. So for that reason, it's common to look at the area normalized emission spectra, which show dramatically the rise in the naphthalate emission corresponding with the decay of the naphthol emission. So I mentioned these are reconstructed spectra. Why are we using reconstructed spectra? As early as 1970, in reports from both North America and from Russia, there were direct recordings of the time-resolved spectra. So using a sampling oscilloscope, they would record the spectra at different times and note that the emission spectra were different. And at a very low temperature, there was no relaxation. At a higher temperature, they observed relaxation. This method isn't used very much because it's limited time resolution. Most of the relaxation times we're going to look at are a couple of nanoseconds, and it's prone to artifacts, and time correlated single photon counting really replace this more troublesome method. So it can be done, but it's not usually done. So let's switch to some biological application. What is the dynamics at the lipid-water interface? Because we just showed emission spectra of protan where the head group would be located at the lipid-water interface. And this is important for a variety of reasons. There's constant motion of lipids and water molecules. Here, there's an interface layer in which some of the water molecules have much slower rotational times. So there's a interface region which is different from the bulk solvent. What's the influence of ion and peptides on this interface? And one of the examples I really like to mention is protein folding, because if you consider the protein folding of a beta-baryl protein, you come to the situation where the peptide has a number of regions where they have a hydrophobic surface, and these hydrophobic surfaces can gather together in the membrane and then release the beta-baryl protein. So motions in the membrane interface and the membrane interior are actually important for protein folding. So as our first example, let's look at the time-resolved decays of this molecule, TNS, which is we've seen before, and when it's bound at the interface of lipid vesicles. And what we find is, it was fortunately what we expected. We find on the short side of the emission spectrum, there's a more rapid decay because the fluorophore is decaying both by emission and by going into the longer wavelength state. And on the red side or longer wavelength side of the emission, we see a rise time. It's not very evident, but it is there. And a longer apparent lifetime because the relaxed state has to be populated from the unrelaxed state. The time-resolved emission spectra in this particular case didn't shift by a great deal, but it shows that when you have this molecule and membrane interface, it is responding to the dynamics at the interface. How do you analyze the time-resolved data? One way of looking at it is to look at the time course of membrane relaxation. So over time, we've plotted the emission maxima here, and we see the emission maxima decays and becomes constant. So the relaxation time is about 2 nanoseconds. And if you're above the phase transition, it decays to a lower energy state. But in both cases, the relaxation time is about 2 nanoseconds. And it would have been too fast for the sampling oscilloscope available, at least in 1970. The other thing we look at is the half-width. And in this particular case that we showed in the previous slide, the half-width stayed constant with time, which means that this was really sort of a continuous relaxation, or spectrally behaved as a continuous relaxation. The next case we want to look at is a different probe, which we call PATMAN, also in lipid vesicles, above and below the phase transition, but this time it's done in the frequency domain. And what motivated me to do this experiment is I read a paper by sort of a prominent person in the area of fluorescence, and he made the statement, time-resolved spectra could never be obtained using the frequency domain. So I thought it could, so I had to prove him wrong. So let's look at the frequency response. As you might remember, we can use either the phase or the modulation, and I'll just describe the phase. So the smaller phase angle at shorter wavelengths indicates a more rapid decay at the shorter wavelength, and the higher phase angle at longer wavelengths indicates the time delay due to solvent relaxation. In this particular case, the phase angles exceed 90 degrees, and that's an important observation because that can only happen if there's a negative pre-exponential in the decay. So phase angles above 90 degrees prove that spectral relaxation is occurring during the lifetime of the excited state. So let's look at the analysis of the data for PATMAN in these vesicles. There are time-dependent spectral shifts, both below the phase transition and above the phase transition. The shifts are much greater above the phase transition, meaning that the lipid head groups and water interface could relax more rapidly at the higher temperature. Let's look at the spectral relaxation process. It's not very different in terms of the time scale than what was observed for TNS. The spectral relaxation remains to be about 2 nanoseconds. There's a larger energy decrease at the higher temperature, but the basic relaxation process is on the 2 nanosecond time scale. In this particular case, the spectral half-widths with time were revealing. At the low temperature, we didn't see anything, but the important observation was at the higher temperature, the half width showed an increase. So we look at these spectra over here. See, there's a half width at 1 or 2 nanoseconds. The half width a little bit out is wider, and then it goes back to a more narrow spectrum. So this is proof of a continuous relaxation process. And it's also consistent with a two-state process. So you can't really say which one, but the data do indicate a continuous process. And one last slide, I'd like to do a thought experiment with you, because I don't have all of the data that I need to show this. But instead of time-resolved emission spectra, which we were just looking at, there's something called the decay-associated emission spectra. So that is the emission spectra that has a particular decay time. So we have a mixture of these two fluorophores, and they have a different emission spectrum. Assume that these are just the emission spectra for the moment, not the decay-associated spectra. They have these two emission spectra. If you look at the time-resolved emission intensity, you would see the spectra changing in time, because the time-resolved spectra are dominated by the shorter decay time fluorophore, and at later times dominated by the more slowly emitting fluorophore. And you can take these data, and instead of using the time-resolved data, you can use the amplitude at each particular time, and you can calculate the decay-associated spectra. So the decay, basically the spectra calculated for the 4 nanosecond lifetime and the spectra calculated for the 11.7 nanosecond lifetime agree with the spectra of the two fluorophores that were in the mixture. And like I said, you're using the pre-exponential amplitudes to calculate these spectra. So decay-associated spectra are different from time-resolved emission spectra. Well, that is all I have to say for this lecture, and we hope to see you at a future lecture. Bye.